Let's say we have a weighted graph and a source vertex in the graph, and now we have to find the shortest paths from source to all the other vertices in the given graph. This is referred to as the single source shortest path problem statement. So let's say this is the weighted graph, and it could be, for example, the nodes might represent the cities, the edges might represent roads. So we have to find the costs of the edges, and if they are representing the driving distance between the pairs of the cities, so we have to find the shortest distance from the source to all the other cities. So let's say if this is our source, so then we will have to find shortest distances between B and A, B and C, B and D, B and E, B and F. So the Dijkstra algorithm is one of the algorithms to find this shortest path between the nodes. And in this algorithm, we keep track of the currently known shortest distance from the source to each node. And now, if the algorithm finds a shorter path, then it will update the distance value of the node. It will mark the node as visited and add it to the path. This process will continue until all the nodes in the graph have been added to the path. So let's say we have this weighted graph, and we have all these unvisited nodes A, B, C, D, E and F. So if we have to choose a source vertex, and let's say this is our source vertex A, and now we have to find the shortest path from A to all the other nodes in the graph. So we use a technique which is known as relaxation. So relaxation says that if there is an edge U and V between two vertices U and V, so if the distance of U plus the cost of the edge between U and V, if it is less than the distance of V, then we will update the distance of V and it will become distance of U plus cost of the edge between U and V. So let's say we have chosen this source vertex A. Currently, the distance of other nodes is unknown, so we put in infinite as the distance of these nodes from the source node. And for the source node itself, the distance to itself would be 0. So this becomes our distance vector where the node distances are infinite and 0 if it is a source node. So relaxation technique says that we have to take the direct edges from the node which is currently under consideration. So currently, since A is under consideration, we will take node edges AB and AD. So let's take AB. So the AB, that means U is A and V is node B. So if distance of U, which is 0, plus the cost of the edge between U and V, so this is the edge between U and V, which is 3, if it is less than infinite or not. Yes, it is less than infinite. So now we have to update the distance of node B. So then the node B distance would become distance of U, which is 0, and cost, which is 3. So this would be updated to 3. So we will say that this distance has been relaxed now. Similarly, for A, D edge, now U is A and D is vertex V. So we check whether the distance of U, which is 0, plus the cost between A and D, which is 2, is it less than the current distance of node D, which is infinite? Yes, it is. So we will update the distance of V, and this will become this total of du plus cost of C, U and V. So this is the relaxation technique which will be used in the Dijkstra's algorithm. So we maintain a list of all unvisited nodes and visited nodes. We also maintain an array which is the previous array. So whichever node is being updated from the current node under consideration, we will put the previous node for that. Let's say the value of B was updated from A, so A becomes the previous node of B. Similarly, the value of D was updated from A, so A becomes the previous node of D as well. So this also array will be kept on updating every time we call the Dijkstra's algorithm. So this is the pseudocode for Dijkstra, where we have an input graph G and a source vertex which is S. Now for every vertex in this set of vertices V, we maintain a distance array and we initialize all nodes to infinite because the distance is currently unknown. We also maintain a previous array which we initialize to possibly null. We will add V, all the vertices, to a priority queue because we are maintaining this queue for all the unvisited nodes. Now for the source vertex, we will mark the distance as 0. Now while queue is not empty, that means till all the nodes have not been visited, we will extract the vertex with the minimum distance u from queue. So from queue we will check which vertex is having the minimum distance currently. So that vertex will become u. Now we will start checking all unvisited neighbors of u. So for each unvisited neighbor v, we are going to check its distance from u. So we will compute this distance temp dist, which will be the current distance of u plus the cost of the edge between u and v. Now if this temp distance is less than the distance of v, then we will update the distance of v to temp dist, and now u will become the previous node of v. So once we have done this for all the unvisited nodes, we will return our distance array and our previous arrays. So let's say this is an example graph which we are going to consider. This is currently undirected. We have taken an undirected graph and we will do the same Dijkstra's algorithm for a directed graph as well. So this is the distance array that we are having, and we also are going to maintain an array which is the previous array. So since A is our source node, we will take it out from our queue array or list that we are maintaining, the queue that we are maintaining, and we will mark A as visited. So now we have to apply the relaxation technique for all the edges which are proceeding from A, which are all the nodes which are directly connected to A. So we have A and B and A and D, and now we will see whether we can relax any edge or not. For A and B, we see that 0 plus 3 is less than infinite or not. Yes, it is. So we will update this to 3. Similarly, for A and D, we have seen earlier also that 0 plus 2 is less than this infinite. So we will update this current distance of D to 2. So this is what we have done. We have checked for node B and we have checked for node D as well. And we have marked A as visited. So we will update these values in the distance vector. So now we have these values for B. The current known distance is 3 and the current known distance of D becomes 2. Now out of these, we also say that since B was updated by node A, so B, the previous node of B is A and the previous node of D also becomes A. Now we check this distance vector and see that which node has the minimum known distance. A is already visited, so we do not consider A. Now out of the unvisited nodes, we see that D is having the minimum known distance. So we will select the node based on current known distances and mark it as visited and add it to the path. So D is now marked as visited and added to the path over here. Now D becomes our next node under consideration. For node D, it has direct edges to node B, node C and node F. And now for each of these nodes, we are going to see if the distances can be relaxed or not. So for node B, this is the distance of U, 2, and the cost of the edge is 2. So 2 plus 2, is it less than 3 or not? No, it is greater than 3. So we are not going to update the distance of B. For C, is 2 plus 3 less than infinite? Yes, it is. So we will update the distance of C to 2 plus 3, which becomes 5. For node F, 2 plus 6, is it less than infinite? Yes, it is. So we will update this distance of F also to 8. So since B has not changed its distance, so the previous node of B remains the same. But C and F have been updated by node D. So now their previous node will also change. So we see that the distances of C and F have become 5 and 8 and their previous nodes have become D. Now in this distance vector, now we have to see which node, the unvisited nodes, has the minimum distance. So D is already visited, so we don't check for D, but now we see that B is the node which has the minimum distance. So now we are going to select B, we are going to remove it from this queue, we will mark it as visited. When we go to B and check its direct edges to other nodes, there are two edges between B and E and between B and C. So now we will check whether we can apply relaxation or not. So for node C, 3 plus 1 is less than 5 or not? Yes, it is. So 5 will be relaxed to 4. For node E, is 3 plus 4, is it less than infinite? Yes, it is. So now infinite will be relaxed to 7. So now these become our new distances now, 4 and 7, which have been updated over here. And since C and E were updated because of B, so B becomes their previous node now. Now in the distance array, we again see that C is that node which has the minimum distance over here. So we are going to select C. C becomes our next node to be considered. It will be marked as visited and removed from Q. And now we are going to consider all edges from C. So there is an edge from C to D also, but since D is already visited, we will not consider that edge. We will consider the edge between C and F. So is 4 plus 2 less than 8? Yes, it is. So we are going to relax 8 and now this distance changes to 6. Also because F has been updated, its previous node will now become C. So now you can see that the previous node of F has become C and the distance of F has been updated to 6. Now we will check which has the minimum value. So F has the minimum value. F becomes the selected node now. F will be marked as visited and removed from Q. There is only one edge which is connecting F to any other unvisited node, which is this edge. All the other nodes have already been visited. So from F to E, we have this edge. 6 plus 1, is it less than 7? It is equal to 7. So we need not update the value of the distance of E. We have marked F as visited, and for E, the previous node does not change. Now we have, out of all the remaining unvisited nodes, only E is left. So E is selected. E is also removed from Q and marked as visited. But since E is not connected to any other node, there will not be any change in the distances. So this is our final distance. This is the shortest distance of A from the other nodes, and these are our previous nodes. So this distance array shows that the distance of A to B, the shortest distance is 3. From A to C it is 4. From A to D it is 2. A to E is 7 and A to F is 6. Let's say how do we find out that how do we get this path from A to E? How do we get this distance 7? What path do we need to follow? So we check this previous array. So what is the previous node of E? So we will start from E. So the previous node of E is B. And what is the previous node of A? The previous node of B is A. So this is the path that needs to be followed to go to the shortest path. So we need to go to B, so which will be 0 plus 3 is B, 3, and from B we have to go to E. So this is the path that is being followed, A to B, B to E, and we can see that the distance is 3 plus 4, which is 7, which we had computed. We can find this out for F as well. So let's say what will be the path that needs to be followed if we want to go to F. So F, we have seen that the current distance is marked as 6. Now if we check the previous array for F, the previous node is C, and for C the previous node is B, and for B the previous node is A. So this is the path that needs to be followed to go to F. So it is A to B, B to C, and C to F. And let's say this is 3 plus 1, which is 4, plus 2, which is 6, and yes, we have got this shortest distance from A to F. Now let's take a directed graph and quickly figure out how this relaxation techniques will work in a directed graph as well. So our source node is A. There are edges from A to B and A to C. We are going to maintain our Q and visited Q and Qs. We are going to maintain this distance array where distance of A is 0, distance of other nodes is currently infinite. We are going to apply the relaxation technique over here. So we saw that 0 plus 5 is less than infinite, so this will become 5. 0 plus 1 is less than infinite, so this will become 1. So this is our new distance array now. Now if we select the unvisited nodes with the minimum distance, it is C. So now C is selected. From C we have edge from C to B, and we have to see that we have to keep on track of the directions of the edges also. And there is also an edge which is going from C to E. We cannot consider this edge because it is from D to C. So we have to take only the outgoing edges from C. So now we apply the relaxation technique. So 1 plus 3, is it less than 5? Yes it is. So this is upgraded to 4. 1 plus 12, is it less than infinite? Yes it is. So this is updated to 13. So we have the new distance vector now, and out of the unvisited nodes, the node with minimum distance is B. So B is chosen as our next node. From B we have now outgoing edges from B to D, B to E, and B to C. Now I'll apply the relaxation again. So 4 plus 3, is it less than infinite? Yes it is. So this is updated to 7. 4 plus 20, is it less than 13? No, it is not. So this is not updated over here. 4 plus 2, is it less than 1? No, it is not. So this is also not updated. So only D is being updated over here. So this is our new distance vector. Now if we find out which node is having the minimum distance, the unvisited nodes only. So we see that this node D is having the minimum distance. So this becomes our selected node now. From D there are outgoing edges to unvisited nodes E and F. We are applying relaxation. 7 plus 6, is it less than infinite? Yes it is. So this becomes 13. 7 plus 2, is it less than 13? Yes it is. So this becomes 9 now. So we are going to update these values and this becomes our new distance vector. Our next node is going to be E. So from E there is only one outgoing branch to an unvisited node, which is F. So is 9 plus 1 less than 13? Yes it is. So this is updated to 10. So and now F is our only remaining unvisited node. We mark it also as unvisited, and since there are no other unvisited nodes, this is our final distance vector. So we can see that from A the shortest distance to B is 4, to C it is 1, to D it is 7, to E it is 9, and to F it is 10. And using the technique I explained earlier, you can double check this also. The limitations of Dijkstra's algorithm that it can work only with graphs with positive weights, because when we are updating, the weights of the edges have to be added, and if there is a negative weight in the graph, now once the node has been marked as visited, we are assuming that the current path to that node is the shortest path, but negative weights can alter this decision. Let's take an example. So let's say if this is our graph and we are having negative weights also in this graph. Now these edge weights, like in negative weights in real life examples, they might possibly represent the profit of doing something, maybe in money or maybe in energy. And a negative weight may mean that we are losing money or energy instead of earning it, or instead of having a profit. So let's say this A was our source node, and when we started our first iteration, we visited B and D, and we are applying the relaxation technique. So 0 plus 10, since it is less than infinite, this will be updated to 10. 0 plus 1, since it is less than infinite, this will be updated to 1. Now if we look at these two distances 10 and 1, since Dijkstra is a greedy algorithm, it is going to choose this path, because we know that 10, when anything will be added to 10, it will be definitely more than what will be added to 1. So we choose the current shortest distance, which is 1, and D becomes our next node. Now we will apply, check what are the direct edges. So there is a direct edge to C. So 1 plus 4 is less than infinite. So this becomes 5. Now let's say instead of choosing D, if we had chosen B, so then 10 minus 7 would have given us 3, which would have been the shortest distance to C from A. But because of Dijkstra's algorithm and because of this negative weight, this decision of choosing D and having a negative weight, this altered our decision. So there is a possibility that our decision might change, or this value might change because of these negative weights. That is why Dijkstra's algorithm does not work well with negative weights in the graph. So in our next video, we are going to look at another algorithm which can handle these negative weights as well.